Inside every computer there are millions of tiny switches. Each one is either off or on, nothing else. This chapter gives you the algebra of those two values, 0 and 1, and shows you how real circuits are built from it. Hello and welcome. Let's start this chapter together. It is called Boolean Algebra. Boolean algebra is the mathematics of just two values, 0 and 1. You can think of 0 as false and 1 as true. This is the same on and off idea that logic gave us with propositions. Now we give it a clean algebra with a sum, a product, and a complement. Then we use that algebra to describe the digital circuits that run inside every computer. Let's look at the map of the whole chapter. First, Boolean functions. There we learn the rules of this algebra of 0 and 1. Second, representing Boolean functions. We build a formula for any function, starting from its table. Third, logic gates. We turn those formulas into real circuits made of hardware. There is a fourth topic, minimization of circuits, but we do not cover it here. The photograph is of Claude Shannon. As a young man, he showed that Boolean algebra is the right tool for designing switching circuits. That single idea is the foundation of all digital hardware. Section 12.1, Boolean functions. In this first section, we set up the algebra itself. We meet the three operations on 0 and 1. We say what a Boolean function is, and we collect the rules that let us simplify expressions. Let's look at the plan for this section. First, an introduction to the three basic operations. Second, Boolean expressions and Boolean functions. That is what these operations combine to make. Third, the identities of Boolean algebra. It is a table of rules, a lot like the logical equivalences we already know. Fourth, duality. That is a neat symmetry hiding inside the table. And fifth, the abstract definition, which says exactly what we mean by a Boolean algebra. Keep this list with you as a checklist. Let's learn the three operations. They all work on the set that holds just 0 and 1. The Boolean sum uses the plus sign and it behaves like an OR. 1 plus 1 is 1. 1 plus 0 is 1. 0 plus 1 is 1. Only 0 plus 0 gives 0. The Boolean product uses a dot and it behaves like an AND. It gives 1 only when both parts are 1. Every other case gives 0. The complement is the bar written over a value. It just flips it. Bar of 0 is 1, and bar of 1 is 0. This is the same on and off logic we saw with true and false. Let's work this one at the board. We want the value of 1 times 0, plus the bar of the bracket 0 plus 1. Set it up. There is nothing to substitute. Every symbol is already a 0 or a 1. So we just apply the three rules and we start with the innermost part. Line 0 is the expression we were given. Step 1. The first term is 1 times 0. The Boolean product needs both parts to be 1, and here one part is 0, so 1 times 0 is 0. Step 2. Now look under the bar. Inside the bar we have 0 plus 1. The Boolean sum gives 1 whenever either part is 1, so 0 plus 1 is 1. Step 3. Now take the bar of that 1. The complement flips it, so bar 1 is 0. Step 4. We are left with 0 plus 0, and that is 0. The answer is 0. Now we say what a Boolean function is. Start with the set B, which is just 0 and 1. B to the n is the set of all lists of length n whose entries are each 0 or 1. A Boolean function of degree n takes one of those lists and returns a single 0 or 1. So it is an ordinary function, but restricted to 0 and 1. For example, f of x and y equals x is a Boolean function of degree 2. The table on the right shows that degree 2 function laid out fully. 2 input columns and 1 output column, with 1 row for each of the 4 possible input pairs. This time the function comes as a formula, and we want its full table. Set it up. There are 3 variables, so the table needs 2 to the power 3 rows. That is 8 rows. The formula has 2 parts joined by a plus, so we build each part in its own helper column and add them at the very end. Step 1. Write out every combination of x, y, and z 8 rows in all. Step 2. Add a column for the product x times y it is 1 only when x and y are both 1. Step 3. Add a column for bar z. That column just flips the z column. Step 4. The last column is the Boolean sum of the 2 helpers. It is 1 whenever either helper is 1. Now let's fill it in. These are the 4 rows where x is 1. The 2 middle columns are the helpers, and the last column is the answer. Row 1. X, y, and z are all 1. The product xy is 1. Bar z is 0. 1 plus 0 is 1, so f is 1. Row 2. Now z is 0. The product xy is still 1. Bar z is 1. 1 plus 1 is 1, so f is 1 again. Row 3. Now y is 0, so the product xy is 0. And z is 1, so bar z is 0. 0 plus 0 is 0. This is the first row where f is 0. Row 4. Y is still 0, so xy is 0. But z is 0, so bar z is 1. 0 plus 1 is 1, so f is 1. And a shortcut worth seeing. While x is 1, the product xy is just y, so in this half of the table, the function is simply y plus bar z. Now the 4 rows where x is 0, something simple happens. Row 5. X is 0, so the product xy is 0. Z is 1, so bar z is 0. F is 0. Row 6. The product is still 0, but z is 0, so bar z is 1. F is 1. Row 7. The product is 0. Z is 1, so bar z is 0. F is 0. Row 8, the product is 0. Z is 0, so bar z is 1. F is 1. Look at what happened. Once x is 0, the product xy can never be 1. So the whole function collapses to bar z. That is why the last column just copies the flip of z. 2 definitions let us compare functions. First, equality. 2 Boolean functions are equal when they give the same output for every possible input, not for most inputs, for every input. 2 expressions that look different but are always equal are called equivalent. Second, the complement of a function. Take the function, then flip its output in every row. That flipped function is written f with a bar over it. We can also add and multiply 2 whole functions. Their Boolean sum adds the outputs row by row. Their Boolean product multiplies the outputs row by row. So there is nothing new to learn. You take one input, you look up what f gives, you look up what g gives, and you combine those 2 bits with a rule you already know. We say the sum and the product are done pointwise, which just means one input at a time. Let's count the Boolean functions of a given degree. Set it up. Think of a function as a filled-in table. The input side is always the same, so the only freedom is in the output column. Counting functions means counting ways to fill that column. Step 1. How many rows are there? Each of the n inputs can be 0 or 1, so by the product rule there are 2 to the n rows. Step 2. How many ways can we fill one output entry? 2. A 0 or a 1. Step 3. Now the product rule again, over all 2 to the n rows. 2 choices each time gives 2 raised to the power 2 to the n, that is the answer. 2 raised to the power 2 to the n grows terribly fast. Let's see it in real numbers. Degree 1 gives 4 functions. Degree 2 gives 16. Degree 3 gives 256. Degree 4 gives 65,536. Degree 5 is already over 4 billion. And degree 6 has 20 digits. Each step up in degree squares the count, so we can never hope to list them all. We need formulas instead, and that is what the next section gives us. There are exactly 16 Boolean functions of degree 2, so we can lay every one of them out. These are the first 8. The 2 left columns list the 4 possible input pairs. Then each of the other columns is one complete function. You read a function down its column, not across. Those 4 bits are the function. For example, f1 holds a 1 in every row, so f1 is the function that always returns 1. And f8 holds a 1 only in the top row, where x and y are both 1. That is the in function. And these are the other 8. The second half is the first half turned upside down. F9 is the exact flip of F8. F10 is the flip of F7, and so on. Some columns have famous names. F9 is 1 whenever x and y are not both 1. That is the NAND function we meet later. F16 is 0 in every row, so it is the function that always returns 0. Every degree 2 function you can name lives somewhere in these 2 tables. Together, they are a complete catalog. If these rules feel familiar, they should. We use the very same rules for logical equivalences with and, or, and not. We used them again for sets, with union, intersection, and complement. Only the symbols changed. Read them one by one. The double complement law. A double bar cancels, so bar of bar x is just x. The idempotent laws. Adding a thing to itself or multiplying a thing by itself gives the thing back. The identity laws. 0 is the identity for the sum, and 1 is the identity for the product. The domination laws. 1 swallows the sum and 0 swallows the product. And the commutative laws. Both operations can be written in either order. Now the second half. The associative laws say brackets do not matter when the operation is the same all the way through. The distributive laws are the surprise. In Boolean algebra, the sum distributes over the product as well. Ordinary arithmetic does not allow that. De Morgan's laws tell you how a bar moves across a bracket. The bar splits and the operation flips. The absorption laws that a whole term vanish. And the last line says a variable plus its own complement is always 1, while a variable times its own complement is always 0. Look at that table again, and you will see a lovely symmetry called duality. The dual of an expression is what you get by swapping every plus with a dot and every 0 with a 1. You leave the variables alone, and you leave the bars alone. Now notice that the identities come in pairs, and each member of a pair is the dual of the other. The idempotent laws are a pair. The identity laws are a pair. So you really only need to remember half of that table. The other half you can build yourself. Let's take the dual of 2 expressions. Set it up. There are only two swaps to make. Plus becomes dot and dot becomes plus. 0 becomes 1 and 1 becomes 0. Bars stay, variables stay, brackets stay. Step 1. Take x times the bracket y plus 0. Inside the bracket, the plus becomes a dot. Step 2. Outside the bracket, the product becomes a sum and the 0 becomes a 1. So the dual is x plus bracket y times 1. Step 3. Now the second one. Bar x times 1 plus the bracket bar y plus z swap every operator. The outer plus becomes a product, the inner product becomes a plus, and the plus inside the bracket becomes a product. Step 4. Finally swap the 1 for a 0. The dual is bracket bar x plus 0 times bracket bar y times z. Let's prove one identity in full. We take the distributive law. X times the bracket y plus z equals xy plus xz. Set it up. There are 3 variables, so the table has 8 rows. The plan is to build the left side and the right side as 2 separate columns, and then compare them. Step 1. First the 3 small pieces. A column for y plus z, a column for xy, and a column for xz. Step 2. The left side is x times y plus z, so multiply the x column by the y plus z column. Step 3. The right side is xy plus xz, so add the last 2 helper columns. Step 4. Then compare. If those 2 columns agree in all 8 rows, the identity holds. Let's fill it in. These are the 4 rows where x is 1. The last 2 columns are the 2 sides we want to compare. Row 1. Y and z are both 1, so y plus z is 1. Xy is 1 and xz is 1. The left side is 1 times 1, which is 1. The right side is 1 plus 1, which is 1. They agree. Row 2. Z is now 0. Y plus z is still 1. Xy is 1, xz is 0. The left side is 1. The right side is 1 plus 0, which is 1. They agree. Row 3. Y is 0 and z is 1. Y plus z is 1. Xy is 0, xz is 1. The left side is 1. The right side is 0 plus 1, which is 1. They agree. Row 4. Y and z are both 0. Y plus z is 0. Both products are 0. The left side is 0 and the right side is 0. They agree. And you can see why. While x is 1, multiplying by x changes nothing, so both sides are simply y plus z. Of course they agree. And these are the 4 rows where x is 0. They are quick. Row 5. X is 0, so xy is 0 and xz is 0. The left side is 0 times something, which is 0. The right side is 0 plus 0, which is 0. Row 6, same story. Both sides are 0. Row 7, both sides are 0 again. Row 8, everything is 0, so both sides are 0. Now put the 2 halves together. The last 2 columns held the same value in all 8 rows. The 2 sides never disagreed, so the distributive law is proved. A table is not the only way to prove an identity. This time we prove one with algebra. The target is the absorption law. X times the bracket x plus y equals x. Set it up. No table. We rewrite the expression, one named law per line, until only x is left. Line 0 is the expression we start from. Step 1. The distributive law. Distribute the x over the bracket. We get x times x plus x times y. Step 2. The idempotent law. It says x times x is just x. So the first term becomes a plain x, and we are left with x plus xy that already looks close to the answer, but we cannot simply drop the second term. We have to earn it. We stopped at x plus x, why now we finish it. Step 1. The identity law used as a small trick. Write that lone x as x times 1. We may because multiplying by 1 changes nothing. Step 2. The distributive law. Now both terms carry an x, so pull the x out in front. We get x times the bracket 1 plus y. Step 3. The domination law. It says 1 plus anything is 1, so the bracket collapses to 1. Step 4. The identity law again. X times 1 is x. We are done. X times the bracket x plus y really is just x. That is the absorption law proved with nothing but named identities. Now the abstract definition. A Boolean algebra is any set B with two operations. One is written as a V and it acts like the sum. The other is written as a wedge and it acts like the product. The set also has two special elements, 0 and 1, and a complement. It must obey these laws. First, the identity laws. xv0 is x, and x wedge 1 is x. The complement laws. xv bar x is 1, and x wedge bar x is 0. The associative law for the v. Brackets do not matter. And the associative law for the wedge, in exactly the same way. The commutative laws. Either operation can be written in either order. The distributive law for the v over the wedge. And the distributive law for the wedge over the v. Notice we never say what the elements of B are. That is the whole point. Any set of any kind counts as long as its operations obey these laws. The point of the abstract view is that many different things obey the same laws. We have already studied two of them. First, propositional logic. Take the propositions with and, or, and not, and with true and false as the two special elements. That is a Boolean algebra. Second, sets. Take all the subsets of a universal set with union, intersection, and set complement. The universal set and the empty set are the two special elements. That is a Boolean algebra too. The small table shows how the three languages line up. The sum, the product, the everything, and the nothing each have their own name in all three columns. Same rules, different clothing. So anything you prove about a Boolean algebra is at once a fact about logic and a fact about sets. Section 12.2, representing Boolean functions. In the last section, a function was often given by a table. Now we go the other way. Given the table of any Boolean function, we build a formula that produces it. We also ask which small sets of operators are enough to build everything. The plan for this section is short. First, sum of products expansions. That is a recipe which turns any truth table straight into a formula. Second, functional completeness. That asks how few operators we really need to build every Boolean function. The recipe for turning a table into a formula has two halves. First half. Ignore every row where the function is 0. Only the rows where the function is 1 matter. Each of those rows gives you one product term, and at the end you add the terms together. Second half. Inside a term you write one letter for each variable. If the variable is 1 in that row, write the plain letter. If it is 0 in that row, write the letter with a bar. That way the term switches on for that row and for no other row. The table on the right holds two functions. F and G, we work them out next. Let's build the formula for F. Run your eye down the F column and look for ones. Set it up. There are 3 variables, so every term will have 3 letters in it. Step 1. There is only one row with a 1. It is the third row where x is 1, y is 0, and z is 1, so the formula will have exactly one term. Step 2. In that row x is 1, so we write a plain x. Step 3. In that row y is 0, so we write bar y. Step 4. And z is 1, so we write a plain z, put them together, and f equals x, bar y, z one row, one term. Now the same job for g, from the same table. Set it up, same recipe, but this time the g column holds two ones, so we will get two terms. Step 1. Run down the g column. There is a 1 in the second row where x is 1, y is 1, z is 0. And there is a 1 in the sixth row where x is 0, y is 1, z is 0. Step 2. Take the second row. X is 1, so write xy is 1, so write yz is 0, so write bar z. The term is xy bar z. Step 3. Take the sixth row. X is 0, so write bar xy is 1, so write yz is 0, so write bar z. The term is bar xy bar z. Step 4. Add the two terms. G equals xy bar z plus bar xy bar z, two ones in the column, two terms in the formula. Let's name the pieces we just used. A literal is a variable or the complement of a variable, such as x or bar x. A minterm is a product that uses every variable exactly once, each one either plain or barred. The special feature of a minterm is that it turns on for one row, and one row only. That is the row which makes every literal inside it equal to 1. So a minterm works like a switch for a single row. When we add up the minterms for all the rows where a function is 1, the result is called the sum of products expansion. Another name for it is disjunctive normal form. This time the function comes as a formula, and we want its minterms. Set it up. We are going the other way now. Before, we had a table and wanted a formula. Now we have a formula and want the sum of minterms. 3 variables, so 8 rows and 3 letters in every term. Step 1. Give each factor its own helper column. One column for x plus y and one column for bar z. Step 2. The function is the product of the two factors, so multiply the helper columns. The product is 1 only when both helpers are 1. Step 3. Then for every row where f is 1, write down its minterm and add them all together. These are the 4 rows where x is 1. The last column collects the minterm when there is 1. Row 1. X plus y is 1, but z is 1, so bar z is 0. 1 times 0 is 0. F is 0, and there is no minterm. Row 2. X plus y is 1. Z is 0, so bar z is 1. 1 times 1 is 1. F is 1. So we write its minterm. X is 1, y is 1, z is 0, giving xy bar z. Row 3. X plus y is 1. Z is 1, so bar z is 0. F is 0, no minterm. Row 4. X plus y is 1. Z is 0, so bar z is 1. F is 1. The minterm reads x is 1, y is 0, z is 0, giving x bar y bar z. Notice the pattern already. Bar z has to be 1, so every minterm will carry a bar z. And these are the 4 rows where x is 0. Row 5. Y is 1, so x plus y is 1. But z is 1, so bar z is 0. F is 0. Row 6. Y is 1, so x plus y is 1. Z is 0, so bar z is 1. F is 1. The minterm reads x is 0, y is 1, z is 0, giving bar xy bar z. Row 7. X and y are both 0, so x plus y is 0. F is 0. Row 8. x plus y is 0 again. So even though bar z is 1, the product is 0. F is 0. 3 rows in the whole table gave us a 1. Now collect the 3 minterms we found. From row 2, xy bar z from row 4, x bar y bar z from row 6, bar xy bar z. Add them, and that is the sum of products expansion of f. Count them against the table. There were exactly 3 ones in the output column, and there are exactly 3 terms in the answer. That is always true, and it is a good check on your own work. Every term carries a bar z, which makes sense, because the original formula had bar z as a factor. There is a second way to the same answer, using algebra instead of a table. Line 0 is the formula we start from. Set it up. No table this time. We keep rewriting until every term mentions all 3 variables. Step 1. The distributive law. Distribute bar z over the sum. We get x bar z plus y bar z. Each term is missing 1 variable. Step 2. The identity law. Slip a 1 into each term. We may, because multiplying by 1 changes nothing. Step 3. The unit property, and this is the clever move. Replace each one by a variable plus its complement, because that also equals 1. In the first term we use y plus bar y, in the second term we use x plus bar x. Now every term can name all 3 variables. Step 4. The distributive law again. The brackets open up into 4 full minterms. Step 5. Look closely. The term xy bar z appears twice. The idempotent law says a repeated term collapses to 1 copy. Cross the duplicate out and 3 terms remain. That is exactly what the table gave us. A set of operators is called functionally complete if you can build every Boolean function using only those operators. Nothing else is allowed. We already have 1 complete set, and we did not even notice. The sum of products method takes any table at all and writes it with products, sums, and bars. So those 3 basic operators are functionally complete. Now the interesting question: can we get away with fewer than 3? The answer is yes, 2 are enough. And with the right choice, even 1 operator is enough. Let's see how. Let's drop 1 operator and check that nothing is lost. Set it up. Suppose we are only allowed the product and the bar. To be complete, we must be able to make a sum out of them. So the job is to write x plus y using only dots and bars. Line 0. Try this expression, bar x times bar y, all under 1 big bar. Step 1. De Morgan's law says a bar over a product splits into a sum of 2 bars. So we get bar of bar x plus bar of bar y. Step 2. A double bar cancels. So we are left with x plus y, that is the sum, built with no plus sign of our own. So the product and the bar are enough. And by duality, the same trick runs the other way. The product equals the bar of bar x plus bar y, so the sum and the bar are enough too. Now the striking one. A single operator can be enough all by itself. It is called NAND, and it is written as a vertical bar between the 2 inputs. NAND of x and y means the bar of x times y, so it is 0 only when both inputs are 1, and 1 in every other case. It is in and gate with its answer flipped. The first trick is to feed the same signal into both inputs. Line 0, x NAND x. Step 1. By the definition, that is the bar of x times x. Step 2. The idempotent law says x times x is just x. So we get bar x, a NAND with both inputs tied together is an inverter. We have made the complement. Now the second trick, and it uses the first one. Line 0. Take x NAND y and feed that one signal into both inputs of another NAND. Step 1. We just proved that a NAND with both inputs the same is an inverter, so this is simply the bar of x NAND y. Step 2. By the definition, x NAND y is the bar of xy, so now we have a bar on top of the bar. Step 3. The double bar cancels, and we are left with xy, so two NAND gates give us the product. Put the two tricks together. NAND alone gives us the complement, and NAND alone gives us the product. And we showed earlier that the product and the complement are enough for everything. So NAND, on its own, is functionally complete. NAND is not the only operator that can stand alone. Its twin works too. NOR is written as a down arrow, and it means the bar of x plus y, so it is 1 only when both inputs are 0, and 0 in every other case. It is an OR gate with its answer flipped. The same two tricks work. Tie both inputs of a NOR together and you get the complement. Then feed x NOR y into a second NOR with both inputs tied, and you get x plus y, so NOR gives us the complement and the sum, and those two are enough for everything. This is not just a curiosity. It is why real chips are often built from one kind of gate only. One shape to design, one shape to test, one shape to manufacture. Section 12.3, Logic Gates. Now we make the algebra physical. Each Boolean operation becomes a small piece of hardware called a gate. We wire gates together to build circuits, and we finish by building adders, the circuits that add binary numbers. The plan for this section. First, the basic logic gates, one for each Boolean operation. Second, how to combine gates into larger circuits. And third, worked examples of circuits, ending with half adders and full adders that add binary numbers. We build every circuit from two kinds of part. A gate takes two or more input bits and produces one output bit. An inverter takes a single bit and produces its complement. The first shape is the inverter, also called the NOT gate. It takes one input x and gives back its complement, bar x. The little bubble on its tip is what marks a complement. Watch for that bubble. The middle shape is the OR gate, with the curved back. It takes two inputs and gives their Boolean sum, x plus y. The last shape is the AND gate, with the flat back and the round front. It takes two inputs and gives their Boolean product, xy. Every circuit in this chapter is made from just these three shapes. Gates are not limited to two inputs. They can take as many as we need. The first drawing is an AND gate with n inputs. Its output is the product of all of them, so it is 1 only when every single input is 1. The second drawing is an OR gate with n inputs. Its output is the sum of all of them, so it is 1 as soon as at least one input is 1. The three dots in the middle mean the pattern continues for as many inputs as we need. Wide gates like these save us from chaining a long line of two input gates. Now we join gates into a real circuit. Gates may share inputs, and the output of one gate may feed into another. This circuit outputs xy plus bar xy. Read it from left to right. The top AND gate takes x and y and gives xy. Below it, an inverter turns x into bar x. A second AND gate then takes bar x and y and gives bar xy. Finally, an OR gate adds the two products together. Building a circuit is always this shape. Make one small piece for each product term, then join the pieces with an OR gate at the end. The two and gates could even share the same X and Y wires. The output would be exactly the same. That circuit had 4 gates. Let's check whether it really needs them. Set it up. There are 2 variables. Look at the 2 turns. Both of them carry a Y, so we pull the Y out and see what is left behind. Line 0 is the circuit's output, xy plus bar xy. Step 1. The commutative law. Swap the letters in each product so the Y comes first. Step 2. The distributive law. Pull the Y out of both terms. What is left inside the bracket is x plus bar x. Step 3. The unit property. It says a variable plus its own complement is always 1, so the bracket is 1. Step 4. The identity law. Y times 1 is Y, so the whole 4-gate circuit computes nothing but Y. You could throw all 4 gates away and run a plain wire. This is why minimizing circuits matters. Let's design a circuit for x plus y, all times bar x. Set it up. There are 2 inputs, x and y. Now look at the shape of the formula. At the top level it is one thing times another thing, so the very last gate has to be an AND gate, and its 2 inputs are the 2 factors. Step 1. Build the left factor x plus y, that is 1 or gate, fed with x and y. Step 2. Build the right factor bar x, that is 1 inverter, fed with x. Step 3. Feed those 2 signals into the final AND gate, 3 pieces of hardware in all. Now let's draw it. And now the drawing. Trace it with your eye. At the top, x and y go into the OR gate, and its output wire is labeled x plus y. At the bottom, x goes into the inverter, and its output wire is labeled bar x. Both wires then run into the AND gate on the right. The final wire carries x plus y times bar x. Each label on a wire tells you exactly what that wire is carrying at that point. Building the labels as you go is the habit that keeps circuit drawings honest. Now a harder one. Bar x times the complement of y plus bar z. Set it up. There are 3 inputs this time, x, y, and z. The top level is still a product, so the last gate is still an AND gate. But each factor now needs some work of its own, so we build from the inside out. Step 1. 2 inverters. One turns x into bar x, the other turns z into bar z. Step 2. Feed y and bar z into an OR gate to make y plus bar z. Step 3. That whole sum sits under a bar, so send it through a 3rd inverter. Step 4. Finally feed bar x and that complement into the AND gate. 5 gates in all. Now the drawing. Follow the 3 inputs. At the top, x meets an inverter and the wire becomes bar x. It runs a long way to the right, all the way to the final AND gate. At the bottom, z meets an inverter and becomes bar z. That bar z climbs up to join y at the OR gate, and their wire is labeled y plus bar z. That wire then meets the 3rd inverter, and the label gains a bar over the whole thing. The 2 long wires, bar x from the top and the complement from the middle, meet at the AND gate. The output is bar x times the complement of y plus bar z. The last circuit puts everything together. We want x plus y plus z times bar x bar y bar z. Set it up. 3 inputs again, and this time each factor uses all 3 of them, so this is the place to use y gates. Step 1. The left factor is x plus y plus z1 OR gate with 3 inputs, does that in a single step. Step 2. For the right factor we first need all 3 complements, so that is 3 inverters. Step 3. Then one and gate with 3 inputs multiplies bar x, bar y, and bar z together. Step 4. Finally, an ordinary 2-input and gate multiplies the two factors. Draw it with 2 input gates only, and you would need 2 extra gates and a much messier picture. Now it is drawn out. Along the top, x, y, and z run straight into the 3-input or gate, and the wire leaving it carries x plus y plus z. Below that, x meets its own inverter, and that wire carries bar x. Y meets a second inverter, and that wire carries bar y. And z meets a third inverter, and that wire carries bar z. Those 3 wires run into the 3-input and gate. Its output is bar x, bar y, bar z. The 2 long wires finally meet at the and gate on the right. Its output is the whole expression. One small aside. This circuit always outputs 0. By De Morgan, bar x bar y bar z is exactly the complement of x plus y plus z, so the and gate on the right is handed some value, and that same value complemented, and anything times its own complement is 0. Now we use gates to do arithmetic. A half adder adds 2 single bits, x and y, and there is no carry coming in. It is called half for exactly that reason. In the top row, both bits are 1. 1 plus 1 is 2, and 2 in binary is 1, 0. So the sum bit is 0 and the carry bit is 1. Next, x is 1 and y is 0. The answer is 1 with no carry. Then the other way round. X is 0 and y is 1, so the sum is 1 and the carry is 0. And in the last row, both bits are 0, so both outputs are 0. 2 outputs from one circuit. That is what we mean by a multiple output circuit. Where do the half adder formulas come from? Straight off the table. Set it up, 2 variables and 2 output columns. So we do the reading job twice, once for each output. Step 1, start with the carry because it is easier. The carry column has a single one in the row where x and y are both 1. That is exactly what an AND gate does. So C equals xy. Step 2, now the sum. It is 1 when at least one of the bits is 1. That sounds like x plus y. Step 3, but careful. The sum is 0 when both bits are 1 and x plus y is 1 there, so we must switch it off in that case. The thing that is 1 exactly there is xy, so we want the bar of xy. Step 4. We need both conditions to hold at the same time, and at the same time means a product. So the sum is x plus y times the bar of xy. Check it against the table row by row, and it agrees everywhere. And now those 2 formulas as hardware. The inputs x and y each split into 2. The upper pair goes into an OR gate, whose wire carries x plus y. The lower pair goes into an AND gate, whose wire carries xy. That wire splits 2. One branch runs straight out at the bottom, and it is the carry. The other branch meets an inverter, and becomes the bar of xy. Then the or output and the inverted product meet at the final AND gate. And that gives the sum bit, 4 gates, 2 answers. A full adder adds 3 bits at once, the 2 data bits x and y plus a carry coming in from the column to the right. 3 inputs means 8 rows. Read the table as plain counting. Count how many of the 3 inputs are 1, then write that count in binary. All 3 inputs are 1. The count is 3, which is 1, 1 in binary, so the sum is 1 and the carry is 1. 2 inputs are 1. The count is 2, which is 1, 0. Sum 0, carry 1. 2 again, sum 0, carry 1. Only one input is 1, the count is 1, sum 1 carry 0. 2 ones again, sum 0 carry 1. 1 again, sum 1 carry 0. 1 again, sum 1 carry 0. And the last row counts 0, so both outputs are 0. That is the whole table. The clever part is that we do not build the full adder from scratch. We reuse the half adder we already have. The first half adder at the bottom left takes x and y. Its sum wire climbs up into the second half adder, and there it meets the incoming carry. C sub I, the sum output of that second half adder, is the final sum bit s. Now the carries. Each half adder also produces a carry of its own. Only one of them can ever be one at a time, so we simply feed both into an OR gate. Its output is the outgoing carry, C sub I plus 1. 2 half adders and 1 OR gate. That is a full adder. Finally, we chain adders to add whole binary numbers. To add 2 3-bit integers, we line up 3 adders, 1 per column. The rightmost column has no carry coming in, so it uses a half adder. It adds the lowest bits, x0 and y0, and gives the sum bit s0 and a carry c0. That carry flows into a full adder for the next column. It adds x1, y1 and c0, and gives s1 and a new carry c1. That carry flows into the second full adder for the top column. It gives s2 and a final carry c2. And that last carry becomes the highest bit of the answer, s3. Let's push real numbers through that circuit. X is 1, 0, 1, and y is 0, 1, 1. Set it up. Bit 0 always means the rightmost bit. So for x we have x0 is 1, x1 is 0, x2 is 1. For y we have y0 is 1, y1 is 1, y2 is 0. And we work right to left exactly as you would by hand. Step 1. The rightmost column goes into the half adder. 1 plus 1 is 2. In binary that is 1, 0, so the sum bit s0 is 0 and the carry c0 is 1. Step 2. The next column goes into the first full adder. It gets x1, which is 0, y1, which is 1, and the carry, which is 1. 0 plus 1 is 2, so s1 is 0 and c1 is 1. Step 3. The top column goes into the second full adder. It gets x2, which is 1, y2, which is 0, and the carry, which is 1. That is 2 again, so s2 is 0 and c2 is 1. Step 4. There is nothing above, so that last carry becomes the highest bit of the answer. The answer reads 1, 0, 0, 0. Check it in decimal. 1, 0, 1 is 5. 0, 1, 1 is 3. 5 plus 3 is 8, and 1, 0, 0, 0 is 8. It works. And that is the end of the chapter.